Welcome back. Today we're going to talk about structures in a very precise mathematical sense. So for me, for this video, a structure is going to be an idealized framework for a building. It's going to be made of bars, which is distinct mathematically in the modeling sense from beams. Those will be covered in a later chapter. Bars are going to be long, stiff rods. They're going to be similar to, we're going to model them very much like springs with a very high spring constant. So they'll never bend, they'll only stretch and compress. And these bars are going to be connected by some universal joints that can swivel in any direction. And in this video, we're only going to treat the two-dimensional case, and we'll treat the three-dimensional case in Structures 2 that's coming up. So again, bars are going to be treated as very stiff springs. They won't bend, they'll only stretch and compress, and I'm going to more or less assume that the spring constant is a very large number. Sometimes I'll set the spring constant to 1 just to scale things to make calculations easier, but in general, if you're assuming that you have a steel bar, it doesn't compress very much. So again, there's only going to be a 2D version in the video. These bars and joints, these structures that we're putting together, will only sit in the plane. Okay, and the general idea is to apply force to the nodes, just like in the springs video. So let's sort out what happens when I apply a force to just one of the ends or to both of the ends of one bar in isolation, not attached to any other bars. So it starts out in some position. There's 2 nodes. Those are the ball joints at the end. And let's say this one is at position A1 and the other one's at position A2. So I'm going to call that one node 1, node 2. And those have x and y coordinates, say A1, B1 and A2, B2. So this is where the bar is when I start. And I'm going to end up applying some force to the nodes. Forces will never, again, act on the bars. They'll only act on the nodes for simplicity. So this moves the bar, and it goes somewhere. And possibly A1 goes to some B1, and I'm going to write that as A1 plus a little multiple of some vector U1. That's the direction. So I'm going to call that epsilon. And epsilon is going to be handy for us later on. And similarly, B2 is going to be the new position of the second node, and that's A2 plus same epsilon times U2. And I'm going to draw in U1 and U2 here in a second. Epsilon is some small number. I'm going to assume that I'm not moving these beams very far. So, okay, so U1 points in the direction of the new B1, and U2 points in the direction of the new B2. And so epsilon's the scaling. How far did it go? And it's not very much. This epsilon is going to be a parameter that I'm going to use temporarily and then throw away. So we're going to be careful. We're going to use it to do one variable calculus on it, and then we're going to drop it. So the question that I want to ask is, in this one bar case, when I move those nodes in those directions, how much does the bar stretch out or compress? And that's what we're going to try to answer in the next frame. Okay, so I've just transferred the same picture that we had on the last frame. So I'm moving one bar from positions with nodes at positions A1 and A2 to positions B1 and B2, and I've got a formula for B1 and B2. I'm trying to compute how much the bar stretches after I do this. Well, the new length is just the norm of the difference between the vectors giving me the 2 endpoints, so that's just the norm of B1 minus B2. And there's nothing for it. I have a formula for B1 and B2. Let's just substitute and write it out. So B1 is A1 plus epsilon 1 epsilon U1, and B2 is A2 plus epsilon U2. I can write this out as a big square root by combining the A1 and the A2 and moving the minus sign through. So I get the norm of A1 minus A2 squared plus 2 epsilon times the following dot product. It's A1 minus A2 dot U1 minus U2 plus epsilon squared times U1 minus U2 norm squared. And this is the new length of the bar after I've moved the endpoints. So the elongation is going to be this quantity, this giant square root mess, minus an additional quantity, the original length of the bar. And I've written squared here, but it should just say A1 minus A2 in norm. So it's not squared there. It's just the length of the original bar. So that's not a linear function. That is a square root of a squared function, and it is not your friend. If you're doing linear algebra, you want something linear. So what you're going to do, what we are going to do, is to assume that epsilon is small enough that a linear approximation to this quantity in epsilon is reasonable. So I'm not going to move very far, is the point. So I'm going to let A be the quantity norm of A1 minus A2, and let B be the quantity A1 minus A2 dot U1 minus U2, and C be the quantity norm of U1 minus U2 squared. Not squared, just regular. So these are all constants in this setting, and epsilon is my variable. So my elongation in terms of this A, B, and C is a somewhat nicer formula. I'm going to name this function g of epsilon. It's the square root of a squared plus 2 epsilon b plus epsilon squared c squared. I'm viewing this minus a. I'm going to view this as a function of epsilon. And I wish it was linear, but it's not. But for small enough epsilon, I can approximate it by a line using the techniques of calculus. I'm going to take the first order Taylor approximation of this function of epsilon, remembering that a, b, and c are constants. So g of 0 is 0. I can plug that in easily enough and find out. And g prime of 0 is also not hard to compute. It's b over a. So I can use one variable calculus to get an approximation of g near 0. So the elongation, as long as epsilon is small enough, should be epsilon times b over a, approximately. Which, remember, b over a, what's that? That's b is a1 minus a2 dot u1 minus u2, and a is norm of a1 minus a2. So all of this times epsilon, as long as epsilon is small enough. Okay, so this is just the same picture as I had before. Node 1 is the top node, and node 2 is the bottom node. I'm going to move it with my green wiggly arrow to some new position, and the stretch is this E, this elongation. So there's a unit vector hiding in this formula. If you set n to be a1 minus a2 over its norm, the norm of a1 minus a2, well, then that's the unit vector that points from a2 to a1 along the bar, then, along the first position of the bar. So it points from a2 to a1. And using this, it's a vector of length 1, that's n. This vector is going to let us simplify our formula. It's going to look all of a sudden quite nice. So elongation is just epsilon times this this unit vector n dot u1 minus u2. But epsilon here, like I said, we were going to discard it. It's just a dummy variable that lets me do my one variable calculus. It's safe to assume that u1 and u2 are very small in norm, and get rid of epsilon altogether. I don't need this variable. So assume that u1 and u2 are small, let's say in length, and then you can write this elongation e as n dot u1 minus u2. And it's going to be convenient to break that up as n dot u1 minus n dot u2, and I'll try to show you why in this picture. So again, here is the same bar that I've been drawing, and here's an arrow that points toward node 1, and there's an arrow that points toward node 2. So this thing, or rather the absolute value, okay, so this arrow, the length of this arrow is the absolute value of n dot u2. The point is that n dot u2 is the component of u2 that points in the direction of node 2, and n dot u1 is the component of u1 that points in the direction of node 1. So in short, n dot ui is the component of u that points toward node I, ui. And again, those should be in absolute values. The n dot u1 and n dot u2 that I've drawn, those are the lengths of those arrows, the absolute values. So the point is that these are exactly the component of the displacement vector that points toward node I. Okay, so now let's transition to having lots of bars and lots of nodes. And the question that I need to ask is, I how can we relate displacement to elongation here? So let's say that I have m bars, and they connect n nodes together. Again, these nodes are universal joints that swivel in any direction, and the bars are like very stiff springs that don't bend. So the elongation vector, the vector full of elongations of each bar, should be related to the displacement vector, the vector full of displacements, by some linear equations. And the question is, well, what matrix expresses that? So let E be this elongation vector. It's got m elongations in it for the m bars that we have. That is a vector in our M. And let U be the displacement vector that's got, well, I've got n nodes, so I must have U1 through UN, but these entries here are vectors, because U1 through UN are vectors in R2. So this U is somehow in R2n. And the best way to see this is in a short example. So if each UI is, say, xi, yi, remember that UIs are vectors, because they tell you where, in what directions you're displacing the node, and there's two directions for it to go. So if UI is xi, yi, then this U now gets to be, well, x1, y1, x2, y2, x3, y3, and so on, all the way down to xn, yn. So I think of making sort of a block vector, pairing off pairs of coordinates within one long column vector. So in order to get at the matrix A that relates the elongations to the displacements, I think it's best if we look at an example. So let's make a triangle. I have 3 nodes, and I make this very simple structure by, let me place, let's make a little teepee, more or less. And you sort of imagine this is floating in space. Those 2 bottom nodes are not down in any sense. There's no gravity acting just yet. So I'm going to place the first node at 0, 0, the second node at 1 over 2 root 3 over 2, and the third node at 1, 0. So these are the vertices of an equilateral triangle of unit length, unit side length. So this I'm going to call bar 1, and so E1 is going to be the elongation of the left-hand bar connecting 1 and 2, and E2 will be the elongation of the second bar connecting 2 and 3. So we had a formula for these E's. So E1 must be N1 dot U1 minus U2. And there's a typo here. So that should be N1 dot U1 minus N1 dot U2. Sorry. Yeah, that's exactly right. And so I split that across. N1 U1 minus N2 U2. And E2 is N2 dot U2 minus N2 dot U3, because E2 connects 2 and 3. So we compute what is N1. Well, that's just not going to be too bad, because we chose these to have side length 1. So it's N1 is going to be the normal vector that points from 2 to 1, and it's just minus a half minus root 3 over 2. I didn't have to normalize it because this triangle had side length 1. I don't know why I wrote n squared there. It's N2. N2 is the other unit vector that points from xy, points from 3 to 2, and I've got a formula for it right here. Okay, so I've transferred that same picture over, and again, my formula for E1 here needs to be replaced. It's N1U1 minus N1U2. So I'm trying to relate my elongations to my displacements. So my displacements are x1, y1, x2, y2, x3, y3. So I put those in a vector, and it's a vector in R6, but I think of it as having 3 groups of things in R2. So U1, U2, and U3 are in blocks in this vector. So I want to multiply by some matrix that will give me my elongations, E1 and E2. So if you think about it, when I multiply the first row, I want to get out E1, but I also want to get out N1.U1 minus N1.U2. So if in the first 2 coordinates I put N1, then that's going to have the effect when I multiply it across of exactly computing n1.u1. And because I want to have minus n1.u2, I apply an extra minus sign in the second pair of columns, and then 0, because that's all it. So when I multiply that first row across my column vector, I'll exactly get E1. That's the formula that I have. Similarly, if I want my E2, I can compute it by taking n2.u2. That's how and I can get that by putting it in the second row in the second grouping, and similarly minus n2.u3. Now, if I wanted to add another bar to this, let's say I add a bar joining node 1 and node 3, then that's very easy to do. All I have to do is add an extra row to this matrix. So what row? Well, I should compute this n3. That's the normal vector that joins node 1 and the unit vector that joins node 1 and node 3. So it's a1 minus a3 over the norm of that, but the norm of it is going to be 1 because this is an equilateral triangle of side length 1. So this is the vector pointing from 3 to 1, and it's just minus 1, 0. And I need to know that E3 is going to be given by n3.u1 minus n3.u3. That's the pattern that we're following because of the physics that was in the previous slide. So now I automatically can fill in the second row because I should put in the group corresponding to node 1, I put n3, and in the group corresponding to node 3, I put minus n3. So let's name this matrix here, let's call it A. It's the same thing we named the matrix in the one-dimensional case with the springs. That's the vector U, and this is the vector E, so we've related E and U via A. E is A times U for this A, and we can always construct an A in this way. So now we're going to think about applying a force to the nodes, and again, just the nodes, not the bars. So, and deal with the balance of forces. So each bar, again, we're modeling as a very stiff spring. And so when I compress the nodes by moving, when I compress the bars by moving the nodes, it's going to push or pull back against the compression of the stretching. So it's a spring. I assume that it's a spring. So let yk be the internal force at the kth bar. So it's either pulling back from a stretch or it's pushing out from a compression. So I'm going to assume it's a spring, so Hooke's law is going to apply. So the internal force should be proportional to the elongation. That's Hooke's law. So Ck is my spring constant, and generally I'll assume it's a very large number because I'm assuming that the bar is like a big steel bar and it resists compression pretty well. Sometimes I'll normalize so that the Ck's are 1 to make my calculations easier, but that's just a matter of fiddling with my units. So I have m bars, and let's say the internal forces of the ith bar is yi, or yk, the kth bar. So I can stick that in the vector, and it's pretty easy to see. It's the exact same thing we did in the springs and masses video. You just can relate the internal force vector to the elongation vector by this diagonal matrix full of the spring constants. So you can name that C, that diagonal matrix C, if you like. Now, we need to balance the forces if I apply an external force to the nodes. Let's say that the kth bar connects two nodes I and j. Well, that means that the force that this yk is exerting specifically on node I, which is going to have to balance against the force that I'm applying, the force will be, if you look at the geometry, minus yk times nk. Yk is a scalar and nk is a vector. On node I, that is the force that's being exerted because my yk is either pushing or pulling. So that means that the force, the external force at the ith node, has to balance all of the internal forces from all of the bars that are connected to the ith node. So if the internal force from one bar, it's at kth bar, at node I is this minus yk nk, and that has to balance with f, Well, then Fi, the force on the external force on the ith node, must be the same as the summation over all of the bars that are attached to node I of these quantities yk, nk, the force that's being exerted on that ith node by the kth bar, add up over all of the k bars that are connected there. Let me erase the little, I don't know why I wrote y as a vector, it's a scalar quantity. So I'm going to elide some details on the force balance, but it's going to turn out, if you run through the calculation, that just like in the one-dimensional case, the force is related, the external force and the internal force are related exactly by the transpose of the matrix that we already wrote down, A. So we end up with E equals AU, Y equals CE, and F equals A transpose Y, which is really just fortunate as heck. So again, you can do that substitution game that we did in the last video. So that means that the force is A transpose times C times A. C, remember, is this diagonal matrix. And A is the matrix that we constructed, times U. I'm going to call that thing K. And in an ideal world, this K thing would be positive definite. But the new wrinkle in this two-dimensional setting is that you can't assume that K is positive definite anymore. It generally isn't. Instead, all we can say about K is that it's positive semi-definite, meaning that if you did an LU decomposition of K, you would find non-negative entries on the diagonal. And K will be positive definite exactly when the columns of A are linearly independent, but we saw that A was pretty rectangular in the example, so it can be pretty hard for the columns of A to be linearly independent. Now, the thing is that lack of linear independence in the columns, or rather linear dependence in the columns, exactly corresponds to members of the kernel of A, and that exactly corresponds, in this case, to rigid motions of our structure. Things in the null space of A exactly correspond to rigid motions of the structure. So again, the best way to see this is by looking at our example from before, our equilateral triangle. So I'll draw the picture one more time. It may not be the last time. I'll draw the picture again. So there it is, there's my triangle, and I've got these nodes. Node 1 is at 0, 0. Node 2 is at 1/2 root 3 over 2. And node 3 is at 1, 0. And you'll recall the matrix that we had, the matrix A that related the elongations to the displacements. I'm going to write it out again here. Again, the point was that I can block off A. The first two columns of A correspond to the first node, the second two correspond to the second node, and the third pair of columns correspond to the third node. So if I look at this matrix, well, it's size 3 rows and 6 columns, so it can't have linearly independent columns. It has to have a pretty big null space. You'll find that the rows are linearly independent, which tells you that the null space has a basis of size 3. And you can believe me when I tell you three independent things that are in here. So 1, 0, 1, 0, 1, 0 is one very nice element of the null space. 0, 1, 0, 1, 0, 1 is another one. And a third element of the null space looks like 0, 0, minus root 3 over 2, 1/2, 0, 1. Check that those are in the null space right now before the video goes on. Okay, so I made this claim that the elements of the null space correspond to rigid motions of the structure. Remember, it's floating in space. It has no forces acting on it. It's not grounded anywhere. If I perform a unit horizontal translation on all 3 nodes, let's say I move them 1 unit to the right, the whole structure should move. That means that I set, say, U1, U2, and U3, the displacements, I set them all to be 1, 0. Well, then when I construct my vector U, I'm going to place 1, 0, 1, 0, 1, 0. And that's exactly the element of that's the first basis element I wrote down. So that thing will span all the horizontal translations. And if I take U1, U2, and U3 to be all the same, and I make them 0, 1, then that is exactly going to give me vertical translations, and it's going to give me the second basis vector I wrote down. because I stack these mini displacements into one big vector. So then the last question that remains is, what is this other thing? What is going on? Well, what's another rigid motion in the plane? Rotation. So I do the same picture again. Now, rotations here are going to be a little bit finicky. They're going to be a little tough because of the linear approximation that we did to compute our displacements. So what I'm going to try to do is to pivot this whole structure around the node 0, 0. So I'm going to fix 0, 0 and rotate that whole triangle counterclockwise, let's say an angle theta. I'm going to rigidly just rotate the whole structure around the first node. Say some small angle, just a little bit, a small rigid motion. Well, what are the new positions of the nodes? So here, I'll draw a picture. The new triangle position will be drawn in green here. So the trouble that's going on is that the nodes are actually moving in a circle when I do this, and well, that's not linear. That's the problem. And so, well, what are the new positions of my nodes? Well, the first node didn't move because I held it fixed and rotated around that spot. So that's not such a big deal. B1 is the new position, and I'll call that, it's the same as the old position, it's 0, 0. B2 is the tricky one. It's not so bad if you apply the rotation matrix that we've talked about to the vector 1/2 root 3 over 2, that was the coordinates of the second node. When you apply that, when you perform that rotation, the new location of the second node is given by this formula, this vector. And for the third node, it's not nearly as nasty looking. It's just cosine theta, sine theta from first year trigonometry. So what are the displacements? Well, the displacement is now B1 minus A1, that's U1, and that's not bad, they're both 0, 0. U2, the displacement of the second node, is not great. It looks like it's B2 minus A2, so I subtract off 1/2 cosine theta minus root 3 over 2 sine theta. That's the first coordinate of B2, and then I subtract off the first coordinate of A2, and so that's minus 1/2. Similarly, with the second coordinates, I get 1/2 sine theta plus root 3 over 2 cosine theta, and I need to subtract off root 3 over 2. So that's the second displacement vector, and the third displacement vector just looks like cosine theta minus 1, comma, sine theta. So what I'm getting at is that if you stack these three things together into one big, tall 6 vector, U1, U2, and U3, that is not going to be an element of the kernel, of the null space of A. And the problem is that I did a linear approximation, and now I'm doing a full, formal, careful, nonlinear rotation. So what I'm going to do instead is to take a tangent approximation, a tangent line approximation, first order Taylor approximation, to these UIs, again, at theta equals 0. So I'm going to do that tangent approximation. So U1, well, it's the vector 0, 0. It doesn't depend on theta. I view these UIs as functions of theta, and I do an approximation of them. So cosine theta looks like 1 near theta equals 0, and sine theta looks like y equals theta near 0, 0. So U2 is quite nice. The 1/2s cancel, and I just get root 3 over 2 theta, half theta, as a minus sign. And U3 looks like 0 theta for small theta. Now, you see that if I pull out theta and stack those three vectors, I have exactly my third basis vector of the null space. So what I'm seeing in the null space is a tangent line approximation to a free rotation around one node. That's my third basis vector. So the basis vectors of the null space of my matrix A correspond to rigid motions in the plane. And you might ask yourself, well, what about other rotations? I might have a rotation around the second node or around the third node. But it turns out that if you do a translation and then a rotation around the first node, you are really doing a linear combination of these basis vectors of the null space. And so all of the rigid motions you can do in the plane are linear combinations of the ones we've already taken care of. So we're going to end the video pretty shortly here. The idea for the next video is to fix a couple of nodes, ground them out, attach them to something. Say we fix nodes 1 and 3 to prevent any rotations or translations. I can fix one node to prevent any translations, but I'll need to fix another node to prevent rotations. I can do that by setting u1 and u2 equal to 0. Remember, u1 is the translation of the first node, and u3, let's say, is the translation of the third node. If I force those both to be 0, then I've attached my nodes someplace. I can see that mathematically by removing the columns of A that corresponded to those nodes, so the first pair and the third pair of columns, drop them entirely, because u1 and u3 had to be 0, so it doesn't matter what's in those columns. I can reduce A into something quite nice. Now it's only 3 by 2, and it's 1/2 minus 1/2, 0, root 3 over 2, root 3 over 2, 0. And if you go back and look at A from before, that's exactly what you get when you remove the first and third pair of columns. Now, the K that you get, A transpose CA, is positive definite. There's no other planar rigid motions that can throw this off. Now, the video is getting a little bit long, so we're going to stop. Next video, we're going to talk about the three-dimensional case and how to deal with inherent structural instabilities, how to detect and deal with inherent structural instabilities in the structure itself.